I lost. Okay. Welcome everybody to lecture 16 of CSE 548, the analysis of algorithms. Let's start things off. First of all, are there any questions about homeworks or anything like that? Okay. The bandwidth contest, we've gotten programs. I've gotten a bunch of programs. We will run them over the weekend, and we'll get them back. Hopefully, we'll get all the programs back next class, along with an announcement of the winners. Some of you may get requests to have to send programs to either me or the TA, depending upon the circumstances. So, if so, read your email and we'll comply. Okay. First question I'd like to do is just take a quick class poll where I think I know what the answer is, but let's just double check. Okay. The question is this: for the next midterm, was originally scheduled for the class before break. Okay. I am willing to put the midterm, okay, if the class approves, I'm willing to have the midterm the Thursday after break. So not the first class when you get back, okay, which I assume would be fairly unpopular, okay, but the Thursday after you get back, okay? So this would mean pushing the midterm back by one logical week and one logical week and 2 physical weeks, okay? How many people would prefer that I keep the midterm where it is? Okay. Okay. How many people would like to see me move the midterm? Okay. 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 Given that I aim to please, okay, the midterm will be put to the Thursday after break. Okay. One trade-off of that, we will finish all the stuff on graph algorithms for that midterm. So everything that we cover on graph algorithms will be on the midterm. Okay. And everything that we cover up to on graph algorithms will be on the midterm. Dynamic programming and graph algorithms. Okay. But you got break to think about it and consult things. Okay, any other questions before we get going?
So that would be the April 11th?
That, I believe, April 11th presumably sounds right, but it's the Thursday. It's not the class right after we get break. It's the Thursday after break. First Thursday after break. Okay? Your homeworks are due the first Tuesday after break. Okay? So you will get your homeworks, have to do your homeworks before you get the have the exam. Okay? Any questions? Very good. Okay. The problem of the day, let's continue on a little bit. The problem of the day, there were 2 problems. One, which I want to talk about right at the beginning, said, give an order n algorithm to test whether an undirected graph contains a cycle. Okay? And we've been talking about depth first search and breadth first search. And either of them can be used comfortably to test whether or not you have a cycle. Why is that? Because if you have a graph, you build the depth first or breadth first search tree, there's no cycle in the tree, but the moment you've got any kind of a back edge, okay, that means you have a cycle in the graph. Why? Because the path, if it's an undirected graph, okay, the path that you have going down and the cycle edge going back forms a cycle. In fact, such a thing is true in a directed graph too. If you do a breadth first search or a depth first search, the moment you have any kind of a back edge, that means you've created a cycle. Further, we could not have had a cycle until we've had a back edge. Why is that? Because everything else in an undirected graph of a search is just going to be a tree edge. And so long as you're not going back to anything, you haven't created a cycle. Okay? So that's an if and only if condition. That should be easy. The interesting thing is that the problem asks for an order n algorithm, okay, rather than an order n plus m, which is claiming that you could actually find a cycle in a graph in time proportional to the number of vertices in the graph rather than the number of vertices and edges. Why don't you have to look at the whole graph to find the cycle? Okay, that's really what it's saying. That seems kind of mysterious. Depth first search takes order n plus m time, where m is the number of edges. The point being that in any tree contains, on n vertices, contains n minus 1 edges. If your graph contains is a simple graph, okay, meaning it doesn't contain any multiple edges, the moment your graph has n edges in the graph, you know it contains a cycle someplace. Okay? And thus, by looking at the first n edges we look at, okay, that's going to be enough to find the cycle. So we can interrupt, if all we're asking to test whether it contains a cycle, we can interrupt that after looking at the first n edges. Okay, and so if we have an adjacency list representation, we don't actually have to cruise through the entire graph to do it. Okay, any questions about that? Okay, question. What? N, okay, now N, we use a convention here, okay, all the time. N is the number of vertices, and M is the number of edges. Okay, and I'm going to use that all the time. Okay, you can remember that, I guess, because N, okay, if you take the number of vertices, we abbreviate that as N, and the number of edges, we abbreviate that as M. Why do we choose those letters? That's convention, and everybody does it. Okay, although there's no logical reason other than the fact that that's the way it's done. Okay, so remember it, and if you don't remember it, ask me. Okay, any questions? Okay, last class we were talking about depth first search. Okay, and some of the properties of depth first search. Okay, depth first search trees and how they behave, and today we're going to go through and see why that's actually important. Okay. The basic principle when we were doing a depth first search, okay, or we're doing a depth first search of a graph, was that we were assigning each edge a classification when we process it according to the tree. In each edge, in each tree, we're going to process each edge. If it's a directed graph, we're going to process each edge once. If it's a directed edge, if it's an undirected edge, we're going to walk over the edge twice. We're only going to be interested in the first time we walk over it. When we do that, we're going to assign each edge a label depending upon where it is in our tree, okay, or where it is in our search. If the edge was in the depth first search tree, meaning it discovered a new vertex, okay, that we call a tree edge. If an edge went back to an ancestor, okay, in the tree, that we call the back edge, okay. If we had an edge that went forward to a descendant, that we call the forward edge. Okay, question? Well, now it depends upon whether or not, the question is this a cycle? Now, this gets really to the heart of whether we're talking about directed or undirected graphs. One thing we showed last class was that if you do a depth first search on an undirected graph, all you have are tree edges and back edges. Okay? If you do it on an undirected graph, this is all that can possibly happen. Okay? That was one of the big powers of depth first search. If we did it on a directed graph, you can have forward edges. Okay? But what does that mean? That meant that there was a directed edge that went like this, and a directed edge that went like this. So we don't have a directed cycle if we have a forward edge. Okay? Because in some sense, remember, we're processing from each vertex, we're processing all the edges going out of that vertex. A forward edge does not create a cycle, necessarily. Okay? Whereas a back edge has to create a cycle. Okay? Because all these edges are labeled going down. Okay? Any questions about that? It's important to get these distinctions right. Okay? And see why they have to happen. Okay? The only other case is if we're not going to a descendant, and we're not going to an ancestor, and we're not going to somebody brand new, we're going to be going to a different node. And that we call a cross edge. Okay? Because we're now going to somebody who's sort of unrelated, well, not a direct relative to us. Okay? So this would be a cross edge. Okay? So what was the interesting point? Okay? It's important to see that when we do any depth first search, every edge is going to be classified as one of these types. So when you do your depth first search, every time you process a new edge, you can label what it is immediately. Okay? And there's only one class any edge can be in. Okay? Any questions about that? Again, the reason why depth first search is going to be important is because these labelings have very, very nice properties. Okay? If you do a depth first search of an undirected graph, every edge is either a tree edge or a back edge if the graph is undirected. Well, why? It can't be a forward edge. Why can't it be a forward edge? Suppose we have a graph like this, and we did a have an edge here, could we possibly, okay, let's suppose we have an undirected graph, and we did a depth first search. Ka-chunk, 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 ka-chunk. Now we visit this edge. Is there any way we would first encounter this edge, the edge 1, 4, coming out of vertex 1 instead of vertex 4? Okay? The answer is no, we can't. Why? Because when we start out at vertex 1, we said explore everything. We start vertex, discover this vertex. Discover this vertex. Check all the edges going out of here before we back up to this. Discover all the edges coming out of here. Okay, go discover something else. Discover everything here before we back up. If we were doing a depth first search, if there was an undirected edge from 1 to 4, we would have first processed it when we were processing vertex 4. And so therefore this would have been a back edge and not a forward edge. Okay? Why is that? That's because we're going to check a look at all descendants out of this before we get back to here. It has to be, if it's an undirected graph, this has to be a back edge and not a forward edge. There cannot be a forward edge. Okay? Any questions about that? Yes? Okay, this was assuming that you evaluated 2 before vertex 4. It is possible if you had evaluated 4, then the tree would have looked a lot different. Okay, they still cannot be a back edge. Okay, on any undirected graph. Okay? There cannot be a forward edge on any undirected graph if you do a search for it. Okay? Similarly, there cannot be a cross edge on an undirected graph. Okay? What is a cross edge? Remember, it's going between two vertices that are not ancestor descendants. Is it possible that we have a cross edge that goes like that? Okay? No, because we would not have, in this case, we would have discovered this, discovered that, checked out all its ancestors, come back here, discovered an ancestor, gone down. Before we leave 2, we would check out all of its possible edges adjacent to it. If there is an edge 1, 5, we haven't discovered 5 yet. So what's going to happen with that edge 2, 5? Before we back up from 2, we would discover it and process it. So our tree would look like this. Okay? That went from left to right would have to correspond to a descendant here. Okay? Any questions about that? That's got to be clear. Okay? There's no way that we could have somehow, if this is an undirected edge, since we were looking at all the vertices going out from here. You can't see that. Okay, that's a good reason. Okay? Since this was a cross, since we were looking at all the edges coming out of here before, that's the nature of the recursion. Okay? We would have to have discovered this edge. Okay? And so our tree would look like this, where vertex 5 would have to hang off 3. Okay? There cannot be a cross edge in an undirected graph. Okay? How many people believe that? Okay? How many people do not believe that? Okay? Everybody believes. Okay? If everybody believes, it is true. Okay? And this, I think, happening. Keep looking at it or get help. That's the fundamental reason why we're going to care about depth first search and why a lot of things are going to work. Any questions? Okay. That said, let's now use depth first search, okay, for a couple of different problems in graph algorithms. Okay? The first problem, okay, is going to be topological sorting. What is topological sorting? Directed acyclic graph, okay, is a directed graph which contains no cycles, okay, no directed cycles. So again, here we've got this would be a directed acyclic graph where there was an edge from here, an edge there, and an edge there, because there is no directed cycle in that graph. This is a non-dag, because this would be a non-dag if we had a cycle. It turns out directed acyclic things, okay, and we'll show you why in a lot of scheduling situations. Directed acyclic graphs model what we're doing, okay? We say a topological sort of a graph, okay, is an ordering of the vertices such that all the edges go from left to right, okay? So let's say we've got this graph 2 and 3. If we order the vertices from left to right, if the graph is an acyclic graph, there is a way, a directed acyclic graph, there's a way to order it such that all the arrows point from left to right. What if we have a cycle in the graph? Okay? Suppose we have a cycle in the graph. It goes from here to here to here to here. Is there a way to order all the vertices from left, all the edges go from left to right? No, because you've got to, you walk along the cycle, eventually you've got to get back to where you're going. And if you keep walking to the left and end up where you started from, the only way you could do that if you went around the world. Okay? So if you're ordering the vertices on a line, if there's a cycle in the graph, okay, you can't have a topological sort. Okay? An if and only if condition. Okay? The graph has a topological sort if and only if it's a directed acyclic graph. Okay? Any questions about that? Well, why do we care about topological sorting? Well, it's a very useful thing to do. Okay? Topological sorting comes up in lots of different problems. And in fact, one of the major things you should take home from here is make sure to recognize when a problem turns out to be a topological sorting problem. Okay? Why might it be useful? Well, one time it's very useful is when you have a scheduling application, okay, where you have a bunch of jobs and certain jobs have to be done before other jobs. Okay? So in the book they give a very cute example, which unfortunately I don't seem to have here, where they took the act of people dressing. Okay? They said, like, for example, I am wearing, okay, pants, I'm wearing underpants. Okay? It would be very embarrassing if I put my pants on before my underpants. Okay? Why? Because, well, it doesn't work. Okay? So if we think about the jobs involved with dressing, we could represent each job by a vertex. Okay? Here we've got pants. Here we've got underpants. Okay? And we know that underpants, putting on the pants has to happen after putting on the underpants. So we could model this constraint by building a directed graph where the vertices are the jobs, the things you want to put on, and there'll be an edge between two things when you have to put one thing on before the other. Okay? What would happen if there was another garment of clothing that, let's say, you had to put on after you put on your pants, but before you put on your underpants? Here we go. Okay. Okay, well, let's take a look. Here's sort of the example from the, let's zoom this thing in. This is an example. Here we've got a directed acyclic graph formed by the way people dress. Okay, you can't put on your belt till after you've put on your pants. You can't put on your pants till after you put on your undershorts. Okay, you can't put on your jacket, they say, until after you've put on your belt. Okay. But there's a certain amount of freedom you have. So there's some constraints in how you dress. Okay? The shirt has to go on before the tie. But there really isn't an issue about a constraint about whether you put your socks on first or your undershorts. Or it doesn't really matter at all when you put your watch on. So the way we can model this situation, again, each possible job gets a vertex. Okay? There's going to be an edge between two things, a directed edge, when one thing has to happen before the other. Okay? What do we want to have happen here? We want to try to find an ordering, since I can only put on one piece of clothing at a time. In order to make sure I don't get into trouble, I need an ordering of these things such that all the edges go from left to right. Because if I have an ordering where all the things go from left to right, such as this ordering, okay, where I put on my socks, then my undershorts, my pants, my shoes, When I have my shoes on, I've already taken care of my socks. If all I just go from left to right, I've satisfied all constraints before I actually do any job. Okay? So it's important to see for a couple things here. If there are no cycles, I can actually get the job done. Okay? That's actually something that's actually maybe not so obvious. If there are cycles, it should be clear I can't get the job done. Okay? Because if I'm waiting, I have to do something before I put on my underwear that depends on me having already had on my underwear, I've got a cycle, I'm stuck. I can't leave the house in the morning. Okay? But if it's in a directed acyclic graph, then the potential exists for a schedule, and in fact there always exists a schedule. To prove that, we'll actually just give an algorithm for finding such a topological ordering. Okay? How many different schedules can there be? Okay? Can someone give an example of a ordering of, let's say, a set of constraints such that there is only one possible way to do it? Okay? What would such a thing be? Suppose I had 3 objects, and I wanted constraints such that there was only one possible way to do it. What kind of constraints would I have to add? Object 1's before object 2, before object 3. Okay? Now there's only one possible way to do it. Okay, so potentially there's only one way to do it. Suppose I had 3 objects and I wanted to have the most number of ways of doing it. Okay, what would be the constraints I'd add then? None. I'd add no edges. If I have no constraints on what I can do them in any order. So potentially there's n factorial different topological orderings. Okay? It all depends upon how many constraints I have and what nature of constraints I have. Whether I have somewhere between 1 or n factorial. Okay? How many people does that make sense to? Okay? How many people are confused? Good. Okay? So the point is that there can be lots of different orderings. So if somebody said, I want to give an algorithm that will print out all possible orderings, what's the worst case time for that? N factorial. Okay? So usually you're only interested in one such ordering. Okay? Or, you know, for practical reasons. Usually you're content so long as you have one such ordering. Okay? And that's why we're looking for an efficient algorithm to find one ordering even though there may be lots of them. Okay? Any questions? Well, that's one application, is the dressing thing. Last week I was visiting Brookhaven National Labs, where they're sequencing, have a project where they're sequencing the bacteria that the DNA of the bacteria that causes Lyme disease. Okay, and I'm working with them on a project with that. And one project that they problem that they have is when they sequence something. Let's say this is the whole DNA sequence. Okay, let's maybe zoom in a little bit. To get the whole sequence, really all that they can do, they conduct experiments to sequence small fragments, okay, at a time. Okay, so they take different pieces and they can sequence, meaning read the strings associated with each of these small pieces. Okay? Now, when they do their experiments, they eventually have to go from these pieces to put them all back together again, because they want the sequence of the whole thing. And it turns out it's for various technical reasons, they can only get sequences of small pieces at a time. Now, what they can do, though, is, for certain fragments, they can say, this fragment has to lie to the left of this fragment. And this fragment has to lie to the left of that fragment. Okay? And so there's certain amounts of constraints that they have, saying that one piece has to lie to the right, to the left of another piece. Okay? Now, sometimes they make mistakes with these errors with these experiments, and they want to be able to tell that. And so they came to me with the following problem. Suppose I have a bunch of these fragments, and I know that certain pairs I want, for certain pairs, I know I want this one to be the left of that one. Can you give me a way to lie them out consistently? Okay, or show me where there might be an inconsistency. Okay? How do I solve this problem? Okay, first of all, any questions about what the problem is? Okay? How would you solve this problem? Okay? Question.
First, try to find out if there's a cycle.
Okay, first of all, we have to build a graph. Okay, what is our graph going to be? What are the vertices of our graph going to be? The different segments will be vertices. There will be a vertex for every segment in the graph. And what are the edges of our graph going to be? Does this guy lie to the left of that guy? Okay. Then what is the answer to their question? Okay.
Well, if there is no cycle in that graph, there's possible.
If there is no cycle in that graph, any topological sort of that graph represents a consistent ordering. Okay? If there is a cycle in that graph, they got trouble. Okay? There's something that they don't know. They made a mistake experimentally. And so as soon as we give them this cycle, they can go conduct more experiments and see where the trouble is. Okay? But this is an example of where, whenever you've got some kind of precedence in scheduling, okay, you can, you can, sort of model that typically as a DAG problem and as a topological sorting problem. Any questions about that, or is that convincing? Question? The fragments. There's going to be, for every one of these little fragments, okay, here's a string, here's a string, here's a string, here's a string. I'm going to have those be my vertices. I'm going to have a directed edge between one and the other whenever one is supposed to be to the left of the other. Okay, and then I'm looking for a way to order the fragments such that any time I say that this is to the left of it, it really is to the left of it. Okay? If not, if it's to the right of it, I have an edge going that way, and I violated the constraint. Any questions? Okay? So that should convince you that this is a useful thing. Okay? Now, how can we test whether a graph is a DAG? Okay, how can we test if there's any cycles? Well, from the problem of the day, it should be clear you want to do some kind of a depth-first search. If we do a depth-first search, okay, basically so long as there are no backward edges, there will be no directed edge. If we do a depth-first search of a directed graph, so long as there's no back edges, there will be no cycles, and it will have to be a DAG. Okay? Any questions? But how do we find this topological sorting? Okay? My claim is the following algorithm will suffice to find a topological sort of any DAG. Okay, what's the claim? The claim is if we take the vertices of our graph and arrange them in decreasing order of depth-first search finishing time, that will give us a topological sort. Okay? Before we look at the proof, let's see if it makes sense. Okay? Let's conduct a depth-first search of a graph just for sort of as a hand-waving thing. Here we have vertex 1. We build a tree, 2. Build another vertex 3. Some back edge. Well, not say no back edge. That would be a bad thing. Okay? From here we get another edge 4. Back. Here we have another edge 5. Another vertex 6. Okay? And since it's a depth-first search, there's no reason why we couldn't have, in a directed graph, a cross edge. Okay? In a directed graph, we're allowed to have cross edges. We're just not allowed to have forward edge. Oh, okay. We're allowed to have cross edges that go one way. Suppose this was our search. This is a directed acyclic graph, correct? If this was the tree we built, okay, and maybe let's add another edge just for good measure. Okay? What was the finishing times of these vertices? Which vertices finished first? Okay, I don't know if this may be easier to say. Which was the last vertex to finish? 1 was the last vertex to finish. Okay, which was the first vertex that we finished with? We went bop, bop. 3 was the first one to finish. Okay? So what's the algorithm say? We want to finish it in decreasing order of finishing time. Okay? So my claim is we're going to put the finishing, that means that the largest finishing time goes first. The earliest finishing time goes last. This says let's put vertex 3 at the end of the line. Correct? Which was the next vertex to finish up? We went up back up to here. We investigated this guy. It had no descendants coming out of it. So the next vertex to finish was 4. Which was the next vertex to finish? 2. Bop. 1. Ka-chunk 5. Ka-chunk 6. 6 went out to 4. 6 had shot its load. What's next? 6 finished up. Which one finished up next? In this case, here's the ordering that we claim we get. Do all vertex edges now go from left to right? Okay. Well, no edges coming from 3. The edge from 2 to 3 looks like that's doing well. The edge from 2 to 4 is doing fine. 1 to 2, that's doing fine. 6 to 4, no problem. 5 to 6, got that one. 1 to 6, got that one. 1 to 5. Sure enough, this is an ordering. Okay? So my claim is this should give us some convincing that there's a relationship between finishing time and where we can stick it. Now, why is that? Let's now just think a little bit more. Why is it that this vertex that was finished could go last? Once a vertex is finished, okay, there is no more edges that are going to later come out of that. Meaning there is no more constraint on this vertex. I mean, this thing about conceptually, there's no later constraints you're going to see on anybody where this vertex is going to tell anybody, I've got to be before you. So with the first vertex to finish, what does that mean? The first vertex to finish means that there is no longer going to be any other constraint where this guy's got to lie to the left of anyone. If there's no more constraint where this has to lie to the left of anyone, without laws of generality, we can stick it all the way to the right. Does that make sense? Okay? There's no more problem. No, this guy has no constraints. Says, I don't care who's after me. If you don't care who's after you, we'll stick you at the end of the line, and you'll be happy. And nobody's going to be made unhappy. Okay? So that's why this algorithm is going to work. Okay? That's conceptually the reason why this algorithm has to work. Okay? What's the proof? Well, let's think about any edge. We're now doing a depth first search on this graph. Let's think of any edge that we encounter. Okay? We're exploring, if we have a directed edge, UV, we're going to encounter it when we're exploring vertex U, because it's a directed edge from U to V. Okay? If V is a white meant that it's the first time we've discovered that vertex. Okay? We're going to start a depth first search of V. Okay? And we're going to finish that depth first search of V before we have finished the depth first search of U. Correct? We can't finish the depth first search of U till after we finish the depth first search of V. Thus, the finishing time of V is going to be earlier than the finishing. Correct? That said, without loss of generality, we can stick it to the right. This algorithm will stick it to the right, and that means this edge will be happy. What if the new vertex V we had was gray? What did gray mean? Gray meant that we had not completely explored it, okay, but we had discovered it. Gray means that it's going to be an ancestor. It yet. It's gray, we discover something out, let's discover something out. If it's gray, our edge is going back to a gray vertex. That means it's a back edge. Can we have a back edge in the depth first search of a DAG? No, it's going to create a cycle. So we don't have to worry about this. That's not going to happen. Finally, suppose that that vertex V is finished. And V is already finished. There's nothing going out of V. Okay? That means that the finishing time of V is earlier than the finishing time of U. Okay? Which means that we would have put V to the right of U by our algorithm. Okay? So that constraint is perfectly fine. That constraint is satisfied. That edge has to go from left to right. Leave this thing, and this is not that hard to convince yourself of. All you have to do is do a depth-first search, one depth-first search via DAG, and you've got your topological sort. You're doing a constant amount of checking of colors at each edge. Okay? The time is the time of the depth-first search. Depth-first search is linear. Topological sort is linear. Okay? Any questions about it? Question?
Yeah, if you do depth-first search, maybe you can go first now directly to the 6 nodes.
You're saying that if we had a depth-first search, you're saying in a different depth-first search, perhaps the tree would have looked different, where 6 would have been up here.
Yeah.
Well, what would that have meant? That would have meant you would have had an edge from 1 to 6, okay, and something from 1 to 5. I'm trying to think now, what would happen? Now discover 6 first. 6 would go to 4 still, okay. There's no edge from 6 to 5, so we would have backed up to 5. 5 would have had a cross edge that would have gone back to 6. The tree shape would have been different. The finishing times would have been different. But that would just lead to a different topological sort. Remember, there's lots of different orderings that are consistent with these constraints. Okay? The important point is once you have for any depth-first search, this is going to work consistently. Okay? So it doesn't matter which edge you come out of. The correctness is still preserved. Okay? Any questions? Question?
Yeah, on the cross edge between 6 and 4 on your original graph,
Right.
Where does that fit in the proof?
Well, what is this edge? What color would this vertex have been?
Right.
No. Black. Because we went bop, 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 nothing coming out, black. So this edge was properly blackened by the time that we this vertex was blackened by the time we had it. So it couldn't have happened. Gray meant that we were going back to an ancestor, which meant we had a cycle. Okay? Any questions? Question?
Just a point I noticed that even if you had traversed to 5 before going to 6 rather than 6 directly, you still have come up with the same topological order in this particular case.
Okay, in this particular case, I might believe that, because you've got a fairly tight constraints here. Okay? But if, let's say, our graph was just something that looked like this, suppose our graph just looked like this, where there were 1, 2, and 3 coming out. It wouldn't make any difference which one of those was first or second or last. Okay, so it depends upon what constraints there are. But once you got the topology, once you got the depth first search, everything is going to be consistent. That's all you care about. Okay? Any questions? Okay? That said, let's look at the second problem of the day. Again, I'm sorry I'm a little bit behind. Some people have actually said that that there's an advantage to looking at the problems before I give the lecture. Okay, it forces you to read the book. Okay, I don't know if I believe that so much. Sometimes you like that. Some of you may believe that, some of you don't. I'll try to get back in sync, but either way. What's the problem? The problem asks for a different topological sort algorithm. Suppose instead that you had could you do a topological sort, okay, in linear time by repeatedly deleting vertices of degree 0. Okay, well, what do you mean by this degree 0? Well, let's say in degree 0. Suppose we've got a depth first a DAG that looks like this. Let's say 1, 2, 3, 4. Okay, you want to add another edge? Fine, we'll add another edge. Okay? Which vertex here is of degree 0? 1 has in degree 0. If 1 is in degree 0, how many predicates does it have? Okay. How many constraints are there? Who's going to complain if 1 is first? Nobody. So why don't we put 1 first, delete these edges, and then ask for some other vertex which is now of in degree 0. Which vertex now is of in degree 0? 2 is of in degree 0 and 3 is of in degree 0. Which one can go first? Doesn't matter. We put 3 next. Which vertices are of in degree 0? 2. Which vertices are of in degree 0? Okay. That is one possible topological sort. Which would the other ones be? 1, 2, 3, 4. Are there any others? Of course not, because everything that we're going to get would have been consistent with the choices that we had. So in fact, all the things we get are possible by all possible choices, orderings of choices of who do we delete next. Okay? So it should be clear that this is in fact the correct algorithm. That by deleting all the vertices of degree 0 first, okay, and proceeding there, that will give us a correct algorithm. Okay? But how would we implement such a thing? Okay? What is the problem? Question? Okay? Well, one possibility is we want to keep track of, we have to keep track of the in degree of each vertex. But more than that, okay, what we really want to be able to do is be able to get which are the vertices of degree 0 quickly. Okay? That's really what the point is. So what we're going to do is there are a couple different ways you can do it. One thing you could do is for every vertex, associate with it its in degree, its current in degree. If its in degree is 0, add that vertex to the list of a queue of things, a queue or a stack of things that we can do at that point. If not, whenever we get find the vertex we want to delete, go to do a search through that number of elements, okay, for all of each of its edges coming out, decrement the count of that vertex degree by 1. Once that got decremented to 0, add it to the list of things to do. Okay? What's the time that will take? Okay? In constant time, we can pull off the next element from the to-do list. What's the in degree of the vertices in the to-do list? 0. We're now going to take all the edges going out of it, deleting them from the graph. For each one, in constant time, when we see the vertex number, we can see what its current in degree count is. If its count is 1 and we're deleting that edge, the count is now 0, and we add it to the to-do list. So in constant time per edge we delete. If it shifts the edge to where we want to go, okay, then we either we'll just delete it and decrement that count, or we'll add it to decrement the count and add it to the list of things. So in constant time per edge, we're doing all the bookkeeping we need. And then in constant time per vertex, we pull out the next vertex that we need. Okay? Question? Okay. There's a question that I think, okay, the question of what it's safe to assume. One thing you have to do, of course, is stock the thing initially. You have to make sure you start with a vertex of degree 0, or all vertices of degree 0. But how much time will it take to find all vertices of degree 0 the first time? Order n plus m, because we can do a depth first search of the graph and count the in degree of each vertex. So we first stock the thing with all the vertices initially of degree 0. Then in constant time per edge deletion, we update what we're doing. Okay? So this gives another algorithm which runs in linear time for doing topological sorting. Okay? Any questions about it? Okay? Specifically about the data structures that we're using to do the bookkeeping. That's sort of the, yeah?
For both versions,
Both versions run in n plus m time. Which one's faster? It's not a relevant question. They're both linear. That's all we can say. Okay? Any questions? Okay? Question? What would happen if there were cycles in a graph? What would happen if there were cycles in the graph? You would eventually get into a situation where you've deleted everything. Okay? What happens if you have a vertex that is a cycle? Are any of these vertices going to ever be in degree 0? No. So if you finish this process and you haven't deleted everybody, what gets left has to have cycles in it. Okay? And so you're stuck. You've got to take care of it. Any questions? Okay? Good. Topological sorting is a good thing to know about. Okay? You can sometimes come out to be a hero pretty easily, just like I did with the biologists. Okay? Any questions? Okay, let's look at another problem that comes up in graph algorithms a lot that can also be solved fairly easily using depth-first search. Okay? Suppose, let's say, you were a terrorist. Okay? That's maybe hopefully a stretch of the imagination. And you wanted to destroy the phone system network. Okay? Here you have a graph where the vertices represent switching stations. Okay? And the edges represent, is there a high-speed link or a link between those two switching stations? Okay? Suppose your goal is to, as a terrorist, what do you want to do? You want to cause trouble. Okay? You want to cause disruption. Which switching station do you blow up in this graph to cause the most disruption? Okay? Is it this vertex? No, because everybody else is happily talking to each other. They couldn't care less about this vertex. Or maybe they could care. It'll decrease maybe the speed at which things, but everybody else. Which vertex do you want to blow away to cause trouble? This vertex, not the vertex of biggest degree, which some people said. Okay? If you blow out this vertex, suddenly none of these stations can talk to those stations at all. The weakest link in the graph is this vertex. Okay? It's possible that there was another vertex maybe with a very high degree. These other guys unhappy, but you wouldn't stop them from talking to each other. Okay? The link that I claim is the most disruptive link, okay, the most disruptive vertex, is the one whose deletion will disconnect the graph. We call a vertex whose deletion will disconnect the graph an articulation vertex. Okay? Why is it called an articulation vertex? I don't know, but that's what it's called. Okay? Okay? If you think about it, it's a cut node. It's the weakest point in the graph. Okay? And in general, there's a whole theory, portion of graph theory, denoted to what they call the connectivity of graphs. How weak is a graph? How many vertices do you have to delete to separate the thing? How many edges do you have to delete to separate the thing? Okay? And it should be clear from this example that connectivity becomes an important thing. Okay? Any questions about it? Are people convinced that connectivity is a useful thing to know about? Okay? Should be clear. Okay? Now, can anyone give me an algorithm, a simple algorithm? Yeah, the first thing when I want to design an algorithm, how would I find a simple algorithm to test whether or not the graph has an articulation vertex, or to find all articulation vertices? Okay? How would I test if first of all, if the graph is connected? Okay? How could I test if I have a graph here if the graph is already separated? Suppose I have a graph like this. It's separated. How could I tell whether it's separated algorithmically? Can't get from one place to another, which would mean what if I did a depth-first search? Right? How would I test whether a graph is separated? Right, if I start a depth-first search from one vertex and it stops before it visits everybody, that means the graph is disconnected. Okay? So my claim is in linear time, using a depth-first search, I can tell whether a graph is connected or not. That said, how can I find all articulation vertices of a graph? Give me an algorithm. Okay? What's an articulation vertex? A vertex whose deletion will disconnect the graph. How could I test?
Well, delete each one and then
One by one, delete each vertex and say, okay, if I delete this vertex, is the graph still connected? Well, do a depth first search. Yeah, it is. Okay, put it back. If I delete this vertex, is the graph still connected? Yes, it is. If I delete this vertex, this edge goes, this edge goes, this edge goes. Is the graph still connected? No, it's not. Therefore, this has to be an articulation vertex, correct? So my claim is, in order n plus times n plus m time, I can find all the articulation vertices in a graph. All the cut nodes, yeah. What? Yes, right, because I continue. If I delete this vertex, there's 2 cut nodes in this one. Okay? So in fact, you're right. If I do it, but if I look through all n vertices, in turn delete them and restore them, okay, and do my search, it should be clear that this much time will suffice to tell which are the bad guys. Okay? How many people see it? How many people do not see it? Okay, everybody sees it. Okay? Now, the amazing thing is, in fact, we can do a much faster job. We can, in fact, find all the articulation vertices using just one depth first search. Okay? How do we do it? My claim the following is true. Okay? If you have any depth first search tree, okay, any vertex, okay, other than the root, is going to be an articulation vertex if and only if that vertex is not a leaf of the tree and some subtree of that vertex has no back edge, okay, incident on a proper ancestor of V. Okay? That's a complicated statement. But let's look at it. Suppose I take this here tree. Here's my graph. I've built a depth first search tree. Okay? Here's my tree. Correct? Is the question of finding an articulation vertex something you want to do on an undirected graph or a directed graph? Okay? Well, we've been talking about it, something that's it's not obviously a directed graph problem. Okay? Maybe there's a version of it that is. But we've got an undirected graph, we'll assume. Okay? What are the possible choices of edges in an undirected graph? If we do a depth first search, we've got tree edges and back edges. These are tree edges. Everything else is a back edge. Okay? One more tree edge. Where's the tree? Here's a tree edge. Okay? Is it possible for any leaf in the depth first search tree to be an articulation vertex? Okay? Why is that? Suppose we snip this vertex away. Is the graph that remains going to be connected? Sure. Why is that? Because just the tree edges are enough to connect everybody. Okay? The leaf nodes are all quite secure. We can bomb them and we don't care. Okay, basically. Okay? Because everybody else, the rest of the tree is holding its structure together. Okay? Any questions about that? Okay? So we know a leaf of a depth first search cannot be an articulation vertex. Okay? What's the other condition? The other condition was talking here about back edges. Okay? Are there any back edges to proper ancestors? The way I'd like to look at it is, suppose I were to blow away a vertex X that was not a leaf. Okay? Might that be an articulation vertex? Yeah, it might, because it might separate these two guys. Okay? What's the only way that we couldn't hold those guys together? Can they be held together by tree edges if we delete an intermediate node? The tree edges won't help us. The only thing that can come to our rescue are back edges. So what do I think of these things? I think of these things as somehow you've got these back edges sort of shooting arrows going back up. The bad guy is trying to make this an articulation vertex. He wants to cut it here. The only way you can hold it together if somebody has shot enough ropes up there to anchor us up to the top. Okay? So the behavior is going to be a function of the back edges. Okay? If we don't have any back edges for a vertex that go above where we are currently, is it possible for that graph to not be an articulation vertex? Or let's put it this way. If we had no arrows going above x, okay, x would have to be an articulation vertex. Why? Because we could delete this thing and there'd be nothing to hold us from falling. Okay? So we need to be, this is what the issue is. Okay? Are there back edges going back to the ancestor? Okay? There are no such back edges. We're stuck. It's going to be an articulation vertex. Further, note that it gets even a little bit more complicated. Here we've got a vertex. Is this vertex an articulation vertex? Okay, take a look at that graph carefully. Is this vertex an articulation vertex? If we delete it, will we disconnect the graph? Well, why? This guy does indeed have somebody to save him, but this component doesn't. None of these vertices have anybody, have any ropes going back to a proper ancestor. So if we cut, what happens if we cut it here? Okay, these vertices will be left hanging, protected by that back edge, but these guys drop down to oblivion. Okay, because there's nobody anchoring them to somebody further up in the tree. So what's the right condition? Okay, the claim here is we're going to have a vertex, a non-root vertex will be an articulation vertex if and only if it is not a leaf and if some subtree of V has no back edges to a proper ancestor. Okay? If we get to a situation where we have some subtree which does not go to a proper ancestor, if we delete this guy, we've separated the graph. Okay? And so my claim is if you're following this discussion, this should now seem to be a condition that makes sense. Okay? Any questions about that? Question?
Is there any reason why they didn't, well, maybe they just wanted to, but is there any reason why you couldn't substitute just an interior node for all that verbiage up there?
Well, an interior node can, the question is, why can't we just substitute an interior node? The point is, certain interior nodes can be articulation vertices, and certain interior nodes may not be articulation vertices.
But it must be an interior node.
It must be an interior node. Because if it was a leaf, we had somebody to punish, okay? I mean, we had somebody to protect. The rest of the graph is connected just by tree edges. If it's not a leaf, to keep it from being an articulation vertex, there have to be enough scaffolding of back edges to keep everybody connected. Okay? Any questions? Question?
How do you tell each node or find out for a given interior node if there are feedback going actually?
Okay. So the first question that comes up here, which, okay, is how do you actually know whether or not there are back edges or not? Or how far up the back edges go? And that's a somewhat trickier issue. Okay? I don't really want to go into the details of that. Okay? Maybe I'll try to give you a hand-waving explanation. Okay? I don't really want to go through the details of that. But what do you do? Well, in a depth-first search, you're visiting every edge and exactly once, correct? Or basically, we're discovering each edge once the first time. When you take a look at an edge, you'll know whether it's a back edge. You'll know further to which vertex it goes. So the way that you could actually do all the bookkeeping, the question is how can you efficiently do bookkeeping to know where back ancestors go? How far back ancestors go? For every edge, okay, for every vertex, we're going to assign it a number depending upon where it is in the depth-first search tree. What was its order that we discovered it? Whenever we have a back edge, we can use that back edge to say, suppose we have a back edge that goes way back to this vertex. That means that we know which ancestor, we know it's got to be an ancestor, And further, because if it's a depth first search, it's got to be an ancestor of everything that's going to be that we encounter somehow. Okay? So the basic idea is we're going to keep track of where we had our furthest edge going back for each vertex as we back up. And by simply maintaining that information, in a clever way, we can do the bookkeeping so that the bookkeeping can be done in constant time. Okay? The bookkeeping's a little tricky. Okay? But the important thing to see is that the condition is right. Okay? Question? Well, would the root be an articulation vertex in this one? The answer is yes, because if we delete the root, this guy isn't connected to that guy. Okay? But let's think about it. The condition here, if you says other than the root. Okay? What would the conditions on the root being an articulation vertex be? Okay? When would the root be an articulation vertex? Okay? Question. Okay? Yeah? When there are two branches coming out of it. Okay? Whenever the root has degree greater than 1, it's going to be an articulation vertex. Why is that? Can there possibly be an edge that goes from here? Okay, if we delete the root, can there possibly be any edge from here to here? Why not? Because that would be, is that a back edge? No. Is that a tree edge? It's a cross edge. Can you have a cross edge in a depth first search tree of an undirected graph? No, so that edge doesn't exist. There's nobody to save this guy. Okay? And therefore the root has to be an articulation vertex, so long as it's got degree 2 or more in the depth first search tree. Okay? Any questions about that? These conditions should make sense. Okay? Well, what's the proof? Well, I've basically gone through the proof. Okay? Why this theorem's correct. If V is an articulation vertex, it can't be a leaf. Why? Because if we delete it, if it was an articulation vertex, it would separate two things. Okay? It can't separate other things because of the tree edges, so that clearly can't be the case. What was the other case? Okay? Basically, that if V separates, let's take a look at this picture here. Okay? If V separates x and y, meaning that the leading V would separate these vertices, this must mean that there is no back edge from a subtree of y to a proper ancestor of x. Okay? What? Proper ancestor of V. And of proper ancestor of V. Yes. Well, maybe I don't want to get braver. Okay? Okay? So, again, if these conditions apply, that if we have any non-root articulation vertex, okay, V separating any ancestor, okay, basically, so long as you've got, unless you've got these back edges going back, they can separate them. If once you have that back edge going back, this cannot be an articulation vertex separating those things. Okay? That's the basic, that's the idea. Okay? We may have to do the proof a little bit more carefully. But the argument that I gave you is the argument why this has to work. And that can just be turned into a proof with a little more verbiage. Okay, if you want a really technical proof. Okay? Any questions? Okay? Now the bottom line is, as was asked, how do you actually do the bookkeeping? Let's think about what would be a trivial way to implement this algorithm. Okay? Question mark.
Well, if you have a back edge, you just traverse down the tree and always say, okay, on that one side, there is a useful back edge.
Right.
You have the long one going up, and you can say, well, the root, the X node, and the one on the left.
Right.
No, not the X node and the one below.
Right. So basically you're saying that what you're saying is that this back edge, okay, means that these guys are accounted for, as far as we're doing. Right.
And then you also have to have a field for, say, to the right.
Right. And so basically what you want to say is we want to make sure that basically every vertex has to be accounted for. It should be clear that you can do that in a complicated way. Okay? The truth is that by doing the bookkeeping in a clever way, this can be done in linear time. If you want to see how to do it, look it up in the book. Okay? What's more important is to see why the condition actually holds. And that's what I wanted to. Now you know why it works, and the rest is just being clever. Okay? But details to be clever. Okay? Any questions? Okay? Now what's interesting about this is you could also do some other things. Okay? Not just testing whether a vertex is an articulation vertex. There's other things that you could find out in the exact same way. Sometimes we want to know whether an edge is a bridge. We call an edge a bridge if that edge will delete the, deleting that edge will delete the, will disconnect the graph. Okay? What would be the right condition on an edge being a bridge? Well, if a vertex is, if an edge is a bridge, both of its edges, for incident vertices, have to be articulation vertices. But does it work the other way around? If you have an edge, both of whose vertices are articulation vertices, is that edge a bridge? Not necessarily. It's a little more complicated. Here, these are both articulation vertices, okay? But they have no impact on whether that's a bridge or not, okay? Bridges could be found in a similar way doing the depth-first search, okay, by taking a look at these conditions and defining that properly. So a lot of different connectivity problems basically fall down to doing the same kind of thing. Okay? Any questions? No, this is a component. There's stuff in here. But always what I wanted to say is here's a situation where you've got a, let's say here's a case where you've got a vertex. Let's say here you've got, okay, what am I saying here? Here you've got a case where deleting this vertex will disconnect the graph. Deleting this vertex will disconnect the graph. And yet this guy is not a bridge. That's really what I was saying. Okay? Any questions? Okay? Let's look at one other application of depth-first search where you can start to use depth-first search to solve another important problem related sort of to connectivity. We say that a graph is strongly connected, okay, if and only if there is a path, a directed path, between any pair of vertices. Okay? Think of it in the road network. Okay? It's not enough to just have it in one piece. Okay? If we have a graph that looks like this, again, I'm sorry if it's not visible. You can cruise, if this was a road network, you could drive around here okay. You could drive around here okay. The moment you drove from here to here, there is no legal way to get your car back. Okay? So if we had a road network that was not strongly connected, you would have a lot of cars stuck at one end of the road. Okay? So in a lot of problems, the question of whether you've got strongly connected components turns out to be fairly important. Identifying where the strongly connected pieces are. Okay? I think the travel net application should be obvious. Okay? In certain clustering problems, okay, the strongly connected components, sort of break things into logical clusters. Okay? So it's an important thing to know about. Now, we say that the strongly connected components of a graph, okay, are the partition of the vertices into subsets, maximal subsets, such that each subset is strongly connected. Let's look at this graph in particular. Here we've got a set of 3 vertices forming a cycle, so this is a strongly connected component. But 2 edges coming out of it, no edges going into it. My claim is these guys you can drive between, there's no way to go from here back. So these white vertices form a strongly connected component that you can't make any larger. Okay? Likewise, these 2 vertices, D and G, there's edges going from there and back. So this forms a strongly connected chunk. But in fact, it's larger because here we've got, okay, what I was hoping. Okay, let's just see. Is this strongly connected? Let's put an arrow here just to make sure. Okay? Now it's strongly connected. Okay? You can now drive back and forth between here and that thing. So what the important point is to see that in any graph, each vertex can be in at most in exactly one strongly connected component. Why is that? Suppose we have a graph here. Here is a strongly connected component. You can drive between them. Here is a strongly connected component. You've got a vertex that's in both of these components. Are there two different strongly connected components in this graph? No, because you could drive between any point here and any point here. Why? If I want to get between here and here, I cruise down. There I am. Okay? What? Oh, sorry, you want to shrink it a little bit. Okay? So the point is, the strongly connected structure of a graph, every vertex is in exactly one component. Okay? How many people believe that? How many people don't believe it? Okay, everybody believes. Okay? Now, to identify what the strongly connected components of a graph are, there is an amazingly clever and simple, amazingly clever algorithm that takes linear time to find all the strongly connected components. Okay? What is that algorithm? You call depth first search. You start from, take the graph, call depth first search to compute the finishing time of each vertex. How much time does that take if the graph has n edges and n vertices? N plus n. Compute the transpose graph, okay, of that thing. Meaning that we take the same vertices and we now reverse all the edges. How much time would it take to, given a graph on n edges and n vertices and m edges, represented as adjacency lists, how much time would it take to reverse all the edges? Okay? You do a depth first search. For every edge you encounter, you simply replace it. Okay? How much time will it take to reverse all the edges? N plus m time. Call depth first search, okay, on the transposed graph. Okay? And order the vertices in order of decreasing finish time. Okay? How much time will it take to do the depth first search? N plus m time. Okay? Order the vertices by finishing time. Okay? That will be basically a, you're sorting n numbers, but each number is between 1 and n, so it can be done in linear time. Okay? So, how much time will this take? Time to do the depth first search? N plus m. Okay? The claim is if you do this, the vertices of each depth first search tree, okay, when you've done that depth first search, is going to be a strongly connected component. Okay? So this algorithm, consisting basically of two depth first searches and a transpose, is enough to find all the depth first the strongly connected components. Okay? Does anybody see how this works? Okay, you shouldn't. This is tricky. Okay, this is remarkably tricky. Okay? But let's try to beat together why that might be. Okay? Maybe we'll look at an example just to convince ourselves of what we're doing first. Here is a graph. In fact, this is the same graph that we had before. Sorry, I'm having problems here. Here is the depth first search tree of this graph. What did that depth first search tree look like? Well, there were tree edges. Okay? There were back edges. Okay? There were, well, it was a directed graph, so there could be cross edges. Okay? There could be edges that go from here to here. In a depth first search tree, there could be no edges, cross edges that go from right to left, from left to right, because if so, we would have made that a descendant. Okay? But there can be cross edges from left to right. There can be back edges. Okay? There can even be forward edges. Okay? So what does this mean? Suppose we've done a depth first search tree of this graph. Okay? What the algorithm said was reverse all the edges. Okay? And then do another depth first search in order of finishing times. Now, why did it do that? Okay? Maybe we'll have to go and explain the algorithm to see what the magic is. First, let's take a look at some simple properties. I claim if you have two vertices in the same connected component, same strongly connected component, no path between them ever leaves the component. Why is that? Okay. Is it possible that this be a strongly connected component and there be another vertex outside which can go into the component and go out to the component? Okay. Well, if that's true, this guy had better be in the component. Because if you can cruise between any pair of vertices here, you can now take this detour, and this guy can now, you can now go from anybody to here and back. Okay? So in fact, we know that anytime there's a path that reaches a vertex and leaves the vertex, it's got to be the same connected component. A second property that we'll have is that in any depth-first search forest meaning the collection of trees, all vertices in the same strongly connected component have to be in the same tree. Now, why is that? What's going to be true is if you have a depth-first search tree starting from some root vertex, every vertex in that tree can be reached from the root. Does everybody agree? Well, why is that? Because we're starting from here and we're looking at all the edges going out. The vertices we discover in this component were all discovered by a chain of edges going out of it. Okay? So we know that there has to be a path from the root of the tree to all its descendants because all the arrows are going the right way. Okay? So in all vertices in a strongly connected component, if we take a look at the strongly connected component from here, every vertex in there can be reached by it. There might be some extra vertices that can also be reached by it. Okay? But those we can't worry about. So my claim is in any depth-first search forest, all vertices in the same strongly connected component are in the same tree. Now, why were we messing with the transpose? Where did that transpose thing come from? This is clever. When you do a depth-first search tree in a graph, a depth-first search from a particular vertice, we agree that all the vertices that can be reached from that vertex will be in that tree. Correct? What if we reverse all the edges? Okay? Okay? Suppose we now consider a tree and we've reversed the edges. What does that mean? That means that every single vertex can reach the root. Correct? So if in the original graph the depth-first search tree would tell us all the vertices that we can reach, doing a depth-first search from a vertex where everything's been transposed will give us a list of all the guys that can reach us. Okay? How many people believe that? Okay? A few. How many people don't believe it? Okay? Nobody. Okay? Meaning people are losing steam. Okay? But what this claims is when we do a depth-first search in the transpose, we're finding all the guys who can reach us. What is the strongly connected component containing this vertex? It's exactly the set of vertices that can reach us that we can also reach. Okay? Because if everybody can reach us, and we can reach them, any guy can get between any other guy by following these edges. Okay? So we need to know the two things. Who can we reach, and who can reach us? That's why we mess with the transpose. Finally, why do we do our search from... Okay, question?
Yeah, I mean, there were a lot more edges.
There were some more edges.
And if you reverse it, then you still can have from any of the ones within a strongly connected component, you still have a
Okay.
tree.
Conceptually, what are we going to be doing here? We did a depth-first search in our original graph. That's what we had here. This was our tree. When we reversed the edges, we are now going to be able to find out who reached us. What was the basic gist of the algorithm? We wanted to take a look at the oldest finishing vertex. Okay? Okay?
If you reverse the edge, then you don't get who could reach us.
Okay.
You kind of destroy that way.
Let me look at this example, and then it'll be clearer. Okay? Here was the original graph. We did a depth first search. The algorithm said, take a look at the oldest finishing vertex, which in this case was this one. And it said, do a search to find out anybody who could reach us. That's what it meant to transpose. Because this is the oldest finishing vertex, nobody else can reach this guy. That's why the algorithm is working this way. Nobody else, none of these other vertices could reach this vertex, or else it wouldn't have been the start of its route. This is in the original graph, not in the transpose. Okay?
There has to be some kind of a cycle if it's strongly connected.
Okay, but let's take a look at it. Here's a graph. Okay? We've done a depth first search on this graph. This is the last vertex to finish. Okay? What is the connected component, the strongly connected component this guy's in? Well, it's everybody who can reach this vertex who we can reach. Okay? Who can we reach? We can reach all of our descendants. Who can reach us? Well, if we do a depth first search in the transpose, this guy can reach us, this guy can reach us, this guy can reach us, this guy can reach us. This is going to be the connected component. Okay, and we peeled that guy off. What was the oldest remaining finished vertex? This was it. Okay? Which vertices could reach us? This could reach us, this could reach us, this could reach us, this couldn't reach us. So this is going to be our second connected component. Yes?
You sort of distorted it when you wrote over it.
Right.
If you just, let's take the center complex there. If you reverse the arrows, and then we stay in the directed graph, we would go from 5 down to 8, right?
Okay. The question is, think about this conceptually. Okay? Forget about the directions that you can work out afterwards. Okay? By yourself. The important thing to see here is our concept is going to be, we're going to find the last guy, take a look at all he can reach, then figure out who can reach him. The people who he can reach, who can reach him, is going to be that connected component, strongly connected component. And the way to figure out who that guy is by trying to figure out who can reach this vertex. The people who can reach it are the ones who we can do the search from in the reversed graph. Okay? That's the idea. Think about it a little bit. We're running a little late. Okay? And we'll maybe survey this guy quickly at the beginning of the next class. This is clever and tricky. Okay? If you don't understand this, don't worry about it. But do make sure you understand what topological sorting is and why that works. And do make sure you understand what connected component, what articulation vertices are. And do make sure you understand what strongly connected components are, even if you're not confident with the trickiness of the algorithm. Thanks a lot. See you next time.